Hey everyone, my name is Phil, and this is going to be a walkthrough of the sleep analysis program that I created for my lab, which is the Espana Lab at Drexel University. If you're curious to see more about the justification for this project, why it was important to do, you can go to my GitHub page, which is here. And if you scroll down, you'll see some of the projects I'm working on. You could connect with me, you can send me an email, you can go to my LinkedIn page, which is here. Right? And this personal website will just take you back to my GitHub profile. So please connect if you're interested. But all the data we're talking about today, all the code, is in the sleep repository. So if you go to repositories and then sleep, you'll see that there is another README here with some context for the project and a description of what each of the files are. I'm going to be continuously kind of updating this, so don't be surprised if things don't look exactly the same. But today, right now, we're just going to go through this program that I made. And the short version is that we do a lot of sleep studies, but right now we score all the data by hand in 10-second bins. And that takes a really long time when you consider that we get 7+ days of continuous recordings. So we're talking about millions of data points, thousands, tens of thousands of 10-second bins or epochs. So it takes a long time. Also, the second thing, we're using a program right now to do that scoring, which is kind of buggy and out of date, and we're not in love with it. So the motivation for this project was see if we could, one, create a machine learning model to automatically score the data, save ourselves lots of time, and two, create this user interface to kind of facilitate data analysis and data visualization. And that's what we're working with here. So if you have this open, if you're following along, you can click load data. And you're going to be loading, if you want to use the example data I have on my GitHub, example_data.wav. And it'll take a minute to do that. I've already done it here, just because the data files are really big, and these metrics, there's a bunch of metrics that it has to compute to produce these plots. But once you do that, you can click here, and with your left and right arrow keys, you can move through the data in time, right? So this EEG and EMG plot, these plots are showing us the raw data, the raw brain activity, EEG, and muscle activity, EMG, in seconds, right? That's the x-axis. So we have 10-second increments here, 10-second windows that we're kind of moving through. And then each window of EEG that we're looking at, we compute a power spectrum for that. And that's what's shown here at the top right under power spectrum. And the complicated way to think about this is we're converting this signal, this EEG signal, from the time domain to the frequency domain via a Fourier transform, but that's kind of obscure. So I think a simpler, more direct way to think about it is if you zoom in, so we could zoom out, we could zoom in, let's out further, let's zoom in. We can look at this 10-second snippet, right, of the signal, and we see that it's kind of a complicated sort of trace. It's kind of jittery, and it goes up and down kind of slowly, but then there's kind of this fast up and down action. And so the idea with the power spectrum is, can we take this complicated signal and separate it out into its component parts and see, is there a distinct component of this that is just this kind of slower wave signal? Is there a component of the signal that's a faster wave signal? And is what we're looking at here really just a combination of those constituent frequencies? And that is exactly what we're looking at with the power spectrum. So here in the power spectrum for this EEG snippet, we're seeing there's a lot of this kind of low frequency power, right? So there's this kind of slower kind of wave that's making up a big part of this signal. And then there's a little, it goes down a bit, and then up here around like 5 to 10 hertz, there's another kind of peak here. So there's a slightly faster component here that's making up a pretty big portion of the signal. Then beyond 10 hertz, right, these higher frequencies, there's really not much, right? So this is a really valuable tool especially when we're comparing the non-REM to REM bouts, right? When we're trying to distinguish between stages of sleep, because those really differ in the relative amounts of their delta, which is this lower band of power frequency here, and their theta, which is this kind of slightly higher 5 to 10 hertz band of power. So those plots are going to become really important. They're really useful just for kind of taking a look at your data too. So we could, if we wanted to score this by hand, I have that function in here. We can press W to call these windows wake, right? So I'm pressing W, and it's updating the color of these windows. So if we go backwards with the left arrow key, we're going to highlight those windows. You can see they're all green, which is associated with wake. I thought green, go, wake kind of makes sense. And it's also updating at the bottom here this thing called a hypnogram. The hypnogram is literally just a tracking for each of the epochs we scored on the x-axis. What is the score associated with those epochs, right? And so as we move through it with the left and right arrow keys, you can see it's updating and keeping track of where we are. So we press W. If we suddenly come across a file that we think looks like non-REM, which is the first stage of sleep we would go into, we can press E, right? So W, wake, E, non-REM. And I'm not saying necessarily that these are non-REM. I'm just kind of showing you that this function exists. You can see here, these are higher amplitude signals, which would be consistent with non-REM. There's much less EMG activity. There's no spikes. And there's a lot of delta power. So this actually might be a non-REM bout. This one, maybe this one. Maybe this is wake again. Eventually, we'll get to a bout where we think, oh, that's REM sleep. So we would go through wake, then we get to non-REM, and then all of a sudden we would get to REM. So we press R for REM. So just by pressing those 3 buttons, you can hand score all of these files. And if you get to one that you're really not sure what to call it, you can press T, and you can see here, it's updating the hypnogram with an unscored bin. So you do have that option if you want, but most of the time we're just going to be looking at wake, non-REM, and REM. A nice feature here is if you wanted to, you could grab this vertical line in the hypnogram and drag it to an epoch that you've scored. Let's say we want to look here, and when you drop it, it's going to update the EEG and EMG plots and take you to those epochs so you can see the scores. Right, so that's really nice if you're like, oh, I want to take a look at this or that bout. I'm just going to click, drop, and drag and drop, sorry, and everything will update and follow that line. So I like the way this is working. I think it's doing a good job. We can export the scores that we've generated. So if we go over here to export scores, we can say, all right, this is yay, hooray, whatever. And we can put that wherever we want, put it on desktop. So it's saving as a text file the scores that we've generated. And then we can also clear them. It'll ask you, are you sure? Clear them. And then if we said, no, wait, no, I want those back, we can go to load scores. We can go find yay.txt, click it, and bam, they're back. So it's doing a good job of keeping track of the scores, showing us where we are in the data, and I think it's doing a pretty good job. I like the way it's working. But as I said, a big goal for this project, one of the primary goals, was to reduce the amount of time we have to spend scoring the data. Right now, we do it all by hand. This file is a 24-hour file, so there's actually, let's find the last epoch. There's actually 17,568 epochs in this file, right? So it's a lot of data to score by hand. Let's see if we can kind of speed that up using a machine learning approach. So I have this decision tree classifier whose parameters I've saved into a file, and we can load that file. I'm just going to load the parameters of the model. And you can see I used grid search CV to optimize the hyperparameters. And when I evaluated this classifier on the test data, it was 96% accurate. So, and it did a really good job of identifying bouts of REM. So there were a few false positives and false negatives there, which is great. Of course, this model is this page is kind of bare bones. I think there's a lot of things we can add to it, but let's just score the data and see how this model does. So if we go back to the home page, right, we had cleared the scores before we came here. You can see the scores are all populated. So basically this model looked at the data, looked at the power spectrum, took all these metrics in, and then generated a set of scores and displayed them. The hypnogram you can see is all populated, and we can travel through with left and right arrow keys just as we were before and kind of see, okay, do we agree with these scores? And this here definitely looks like a non-REM bout. There's really big amplitude signals here, lots of delta power, no EMG. So we're going backwards now, right? I would agree this is all non-REM. Good job, model. And actually I found an epoch, so we can click find epoch. I found one in this data that I would like to look at because it's a good example of a transition from non-REM to REM. And that's a really important transition that we want to capture. Right, so here we have some non-REM. It's correctly scored as non-REM by the model. We're going to go forward, and then all of a sudden we see, boom, we're getting into these lower amplitude EEG signals, but really big theta power. So look at the power spectrum here. This is a lot of theta, and you can see that in the relative power too. And so I would say this is definitely REM. There's no EMG. Look at that really big theta power, and we're going to go forward, 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 and all of a sudden there's a bunch of EMG, right? So there's lots of theta, no EMG. Next window, bunch of EMG, not as much theta, the animal's awake, right? So the model actually did a great job of identifying this bout of REM, and I think with some improvements, it could do an even better job and behave consistently across animals. Of course, we're going to have to continue to test it, but so far, this is how it's working, and I hope you thought it was cool and interesting. If you'd like to talk to me more about it, please contact me on LinkedIn or via email. Again, my LinkedIn is here. You can connect with me, please, if you're interested. You can send me an email here, philclarkphd@gmail.com, and I'm going to be making updates to these repositories pretty consistently, so keep checking back in for new updates. All right, thanks a lot. Bye.